All right, so today, guys, I want to finish up talking about kind of the root equations. I want to go through some of them, maybe multiple ways, because I want you to start seeing and understanding that, you know, this question might be able to be approached 2, 3, 4 different ways. Hopefully, you start to see maybe the reason why it's nice to foreshadow the amount of work that's going to be involved, because one way might take us 2 minutes, the other way might take us 6 minutes. I also want you to see that, you know, you might think, okay, I need to isolate a root here and start squaring both sides, and then when I get a new line, I always want to kind of compare that to what I started with, because if I square something and I get a new line, but that new line of information simply models what I started with, it's just bigger coefficients, it probably means the route that I'm taking isn't going to lead me anywhere useful, and I probably need to start over, use a different approach. And that's kind of the thing a lot of times, especially early on, when you're just learning this stuff or just revisiting it, you might not know the structure of an equation and what that's going to lead to. You might know this is the structure, these are the rules, but I want you to start thinking consciously about the results that you get line to line, and think consciously about the options you have in approaching questions. I think, and it's not to your fault, but I think in growing up in the 6th grade, 7th grade, 8th grade, 9th grade, 10th grade, okay, not so much in geometry, maybe the 9th or 10th grade, but then when you get back to Algebra 2, you're almost trained to do a procedure of steps and not think about them, okay? Where the further you get into mathematics, the more damaging that is to your success within the algebra, okay? Maybe not so much the success, but the efficiency of your algebra, okay? And there are some things here that we're talking about today that if you just blindly start doing the rules that we've set forth, there will be a couple questions you get absolutely wrong because you're not thinking about what those symbols in front of you are really telling you what's going on. Okay, so we always want to be actively thinking about what we're doing and why we're doing it. It will make a lot of our work a little bit easier. So I think we did this one, right, in class on Monday? Yeah. All right. I'm going to skip example 3 for the moment. If we have time, we'll come back to it. But I think example 3 is just like example 2 once we get that x to the other side. Does that make sense? Okay. So I don't think that's a main priority right now, that example. But I do want to talk about example 4. Okay. Example 4 has 2 square roots, right? This one's different than all the other ones because we've got multiple roots occurring here. You're still going to use the overall approach that I want to isolate a radical. Okay? What's nice here is that one of those radicals is already isolated for us, right? Okay? As we go through the work, remember, we're trying to use inverse operations to make things look simpler. Now, when we go through this, we might get more terms than what we start with. But right now, what's making this problem complex is the double radical, right? Okay, or the 2 radicals. After we do a little bit of work, let's see if that problem starts to disappear. Okay? So I already have this side isolated, it's all by itself. So let's just go ahead right away and square both sides. Square that. Come over here, square that. When I square this side right here, okay, I'm sure we left with the radicator, right? 3x plus 1. Remember what this means. You have a binomial. You have 2 plus root x plus 1 times 2 plus root x plus 1. That means FOIL, right? So I do first times first, which is 4. I have to do outside times outside, which gives me 2 root x plus 1s. And then inside times inside is going to give me 2 more of those. So total gives me 4 root x plus 1. And multiply last times last, so I take root x plus 1 times root x plus 1, and that's just going to leave me with x plus 1, right? An option that you guys have here, because you might think that, you know, if I look at, and this will be something that we do a lot with later on, but I think when looking at 2 plus root x plus 1 times 2 plus root x plus 1, I think that gets kind of ugly. Okay, and trying to foil that and think about keeping things straight. So this is what I like to do. I like to say, okay, well, let's let, I don't know, v equal root x plus 1. So then can I do this? Can I then rewrite this as 2 plus v times 2 plus v? Does that make sense? Foil it out, 4, 2v, another 2v, so that's 4v. And now plus v times v is v squared, right? But what was v? It was this. So let's go plug that back in. Root x plus 1, 4 times root x plus 1. Now if I square that, doesn't the square root go away? And I'm left with just the x plus 1. So it gets me eventually to the exact same thing we got there, right? It's just algebraically writing by hand, maybe it cleans things up a little bit, makes it more obvious what our multiplication is going to look like when we go through that. Regardless of the technique you use though, we should get this. Now, this is what I was saying, this is obviously more terms than what we started with up here, right? Okay? But is it simpler overall because we've eliminated a radical, right? So that's the goal here. Now what we have, we still have a radical, so we play the game over again. We go through the whole process again, isolate a radical, then use the inverse operation to get rid of it. So, we're going to take in, I'm going to move my, we got 4 and 5 here, right? So move that 5 over. With this 1 will give me negative 4. I got this x here. I'll move that over. So it gives me 2x minus 4 is now equal to 4 root x plus 1. Everybody okay with that? Okay. Now, you've got options here. If you're a person that wants to take that 4 as a coefficient of my root, and you want to divide both sides by that, by all means, go ahead and do it. Because everything up there is divisible by 4. Now, the 1 or the 2 is going to give me a fraction, but it's not a terrible fraction. Okay? So if you want to make that 4, that coefficient of the root, if you want to make that, I don't know if I call it a coefficient, that multiple of the root, if you want to take that and divide it out, go ahead and do it. That's fine. You don't have to, though. I'm not going to. And I'm not going to because I know, I'm just thinking ahead, I know that when I square that, it's going to turn into 16, right? I start looking at the left-hand side, and I know when I square 2x minus 4, there's going to be some multiples there, some 16s maybe show up. So I'm just going to leave it in and see what happens. Okay? I think it's going to be beneficial to leave it, but I don't know. If you're a person who says, well, I want to divide everything by 2, that might even be better. Does that make sense? Okay, but it shouldn't matter. You can leave a coefficient here. But now I got to get rid of that root. So I'm going to square both sides. So when I do that, now I get 4x squared on the left minus 16x plus 16. That's what that thing there multiplied by itself will look like. The right-hand side turns into 16, so the 4 squared, and now I square this, right? Gives me x plus 1. Remember when you have like a to the m, b to the n, raised to the c power, so you got a product of things here, right? Raised to a power, you rewrite it as a to the mc times b to the nc, right? And that's what we've done here. We've got 4 to the first, and we have x plus 1 to the 1/2, and we're squaring that. So we're going to take this 2 and apply it to that 1 through multiplication, so I get 4 squared. And then I got to take that 2 and apply it to the 1/2, so I get x plus 1 to the first. Evaluating that, multiplying that out gives me 16 times x plus 1, right? Okay. I like to show that at this stage of your algebra careers, I like to show that kind of stuff Because a lot of times people are going to just say, maybe incorrect algebra because they're not certain on what the rules that we've learned in the past, how we should apply them. We just want to make sure that we're seeing that type of stuff and understand the logic of why I have to square this and why we have to square that, okay, or that root portion. So now, what does this tell me? What's the algebra I got to do there? I would distribute, okay? Because foreshadowing, I could divide both sides by 16, right? And it'd be nice here, it'd be nice here, but foreshadowing, it's not going to be nice there. If I multiply that 16 through, now I got a 16x on that side, right? I got 16x on this side. I'll have a positive 16 on this side. I've got a positive 16 on this side. That's going to be a nice relationship if I FOIL or distribute that through. So I'll do that. 16x plus 16. The real nice aspect of it is that that's positive, and so is that. So they cancel each other out, right? Okay, subtract 16 from either side, it gives me 0 from that aspect. Now if I subtract 16x from both sides, it gives me 4x squared minus 32x equals 0, right? What is nice about that? I can take 4x out of both terms of GCF there. 4x gives me x minus 8. So 4x equals 0, so that's going to give me x to be 0. X minus 8 equals 0, that'll give me x to be 8, right? Okay. Now, the only thing you have to be cautious of is the potential that one or two of those solutions do not work. So when we're done, we're going to take our 0, we're going to come back up to the top, we're going to plug it in. So we get 3 times 0 is 0, plus 1 is 1, right? What's the square root of 1? 1, right? Does that equal 2 plus 1 plus 1 under a root? Oh, sorry, I did that wrong. 0, right? 0 is x. 0 plus 1. Does 1 equal 3? No. So it tells me that this extra solution does not satisfy the original equation. And the reason it doesn't satisfy is because this process of squaring starts to potentially create extraneous solution. Whenever we square an equation, you got to think the potential of extraneous solution. If I plug 8 in, okay, 3 times 8 is 24 plus 1 is 25, right? Gives me root 25, which is 5. Come over here, 8 plus 1 is 9. What's root 9? 3, right? Is that a true statement? Absolutely. So 8 is my only true answer. It's the only one that satisfies the equation. Now, I know we only did one example here. Maybe we look back at some of the examples yesterday or I guess the day before. Just because I find one extraneous solution, just because I found 0 to be extraneous, does not dictate 8 as being a solution. Does that make sense? Okay. And just because maybe I checked 8 first, if I would have done that, if I would have checked 8 first, it does not automatically mean that 0 is extraneous. You have to target both solutions, or however many solutions you have, and check all of them. Okay. I think what happens, and again, it's just the way problems are designed in a textbook, or they're provided in a textbook, is that you get in a habit of finding maybe 3 or 4 questions in a row that when I check the first solution it works, and the second solution is an extraneous one. That's just the nature of how they're set up. It's not done on purpose. But then you get trained and say, okay, I check the first one, it works, the second one doesn't work. And I do that all the time, and I do that incorrectly in certain situations. All right? So make sure that we're always checking those solutions. All right, so there's one down here that we skipped over. Now this is in the section on equations with rational exponents, and it should also actually be in this section where it says equations in quadratic form. There's a couple different ways of approaching this problem here. Okay? And I think one later that we're going to do as well. Okay? So x minus 5 root x plus 6. Okay? I'm going to approach this question using the square root technique. Okay? And the squaring, using the inverse power of 2. And the reason I want to do that with you right now is because a lot of times when people see the symbol of the root up there, they're not thinking all the time about x to the 1/2. Okay? So you see that, so I got to isolate the x, or the square root of x. Absolutely. Let's go ahead and try and do that. So I go x plus 6 equals 5 root x. You guys agree with that? Now what do I have to do to both sides? Square both sides. So it gives me x squared plus 12x plus 36 equals 25x, right? Again, we got square root of 5, gives me 25, square root of root x, gives me just x. Is that now a quadratic equation? So we should be able to move the 25x over. And hopefully you're seeing 9, 4, right? Negative 9, negative 4 gives me 36. The product. We name 13 as sum. So we get x to be 9, we get x to be 4, right? Is everybody okay with that? I know that's fast, but I think we've been doing enough factoring where we can get that. So the first step is really the only thing new that we're trying to target. The thing in the blue there. I got to check myself. I'll plug my 9 back in, so I get 9 minus 5 times root 9, so that's 15, isn't it? 5 times 3. And then plus 6. Does that give me 0? Yeah, so 9 works. Okay, and this is where I'm saying, don't think just because 9 works that 4 doesn't. When I plug in 4, 4 there, minus 5 times root 4, which is 5 times 2, so 10. So right now I'm at negative 6, right? Add 6 to that, gives me 0. So they both work. All right? We do not have a situation where there's extraneous solutions here. Okay? What I want you to understand, and you might be thinking I'm beating a dead horse, okay? But just because the nature of the solutions to question 1, that does not have any impact on the nature of the solutions for question 2 or 3 or 4. Okay? So make sure that you're paying attention to that. Now, if you're a person that says, well, I didn't see it that way. Okay, when I see this question, just because I've done it enough, and things like it enough, I see this. Because I know the benefit, because I've done this math, this algebra a lot, and I've done a lot more courses that have techniques and procedures in them, that with dealing with square roots, it's just a pain in the butt. That symbol is ugly. It's not extremely useful a lot of times. Is that I always convert things to that. Because now, if I do that, I see this. I see that u could be x to the 1/2, and u squared would be x to the 1/2 squared, which is just x to the first, right? So we see that substitution that we've done before. So now could I rewrite this as u squared minus 5u plus 6 equals 0? That's going to be negative 2 and negative 3, right? U minus 2, U minus 3. Now, factored differently than this did here, okay? Because it's obviously a different quadratic, but now I'm solving for U. So I'm going to get U equals 2 and U equals 3. But remember, what was U? It was x to the 1/2, right? So I'm going to write it that way. So I think it makes a little bit more sense maybe in the next step. Remember what we're always trying to solve for is x, right? Not root x. What would I do there in those two things to solve for x? Square both sides. Okay. One of the benefits, I don't know if there's less work there. I don't know if time is saved either way. But I think the benefit of doing the stuff on the right is that the numbers are a lot smaller. Okay. Especially if the original problem would have larger coefficients other than 5 and a larger constant than 6. Maybe the blue technique is a benefit because of the smaller coefficients. Does that make sense, everyone? All right. whatever route you're comfortable with is fine. My fear is though, is that you're gonna learn only one route and just always use that one route. And then you get to a situation at some point when you have to use the blue route. That's the only thing you can do, but you force yourself to only learn the red. Does that make sense? Yeah. And that's something throughout the entire year. Learn 2, 3, 4 different ways of doing something. Try to pick, I'm not gonna say you're gonna be extremely proficient at all 4, but become somewhat understanding of all 4 and it will help you immensely. Yes? Yeah, if we have time at the end. So let's see here. All right, so this one. Again, I look at this one, and I see the x under the root, okay? So I see x to the 1/2 right away. I see minus 3/4 root of x. So I see right there, that's x to the 1/4. And that instantly signifies to me that U substitution is probably my best approach here, okay? So I want to do this a couple different ways, okay? Actually, I want to do this 3 ways, okay? The first way that we're going to go about doing this is not going to produce anything useful, okay? I think algebraically it's important to understand that when I have the 4th root of something, the 4th root is simply just taking the square root of a square root. Does that make sense? Okay. Let's walk through that algebra, why that's true. I don't know why, every day I take my markers back to my desk for some reason. I got to walk back and forth all the time to get them. And I'll do it again here in a little bit. I don't know why. All right, so let's just focus on that 4th root real quick. The 4th root of x. Okay? I want to show you that that is simply the same as the square root of the square root of x. A lot of times we call that kind of a nested radical. Okay? I think about things in nests. They're surrounded, right? Okay? So it's a radical inside a radical. Sometimes referred to as like a composite, or compound radical, something like that. Why are these the same? Is this idea here? Is because if I work from the inside out on this part here, can I rewrite that as x to the 1/2? Can I write that thing right there as x to the 1/2? Okay. I'm going to do that. And I'm going to do something that doesn't make a whole lot of sense really initially, but it is true. I'm going to put an exponent 1 there, right? I mean, I can do, if I wanted to do that like 30 times, I could do that, right? We can do it 1 time here because of the next step. Because if I work from the inside out, I still have this thing there, right? Does that make sense? And I'm just going to call this is my object. I'm no longer going to deal with that 1/2. Because now it's raised to the 1st power and it's taking the square root of it. So that's my numerator and that's now my denominator of my exponent. Does that make sense? So I'm going to rewrite this then as x to the 1/2. That's this. But now I'm getting rid of this root symbol to be that divided by that as my exponent. And I get that. Well, what is that equal to? What do I do with a power raised to a power? I'm multiplying. It gives me x to the 1/4, right? And now if that's an exponent, a rational exponent, we know we can always convert that and say, well, that denominator is your root or your index. The numerator is the power of your radicand. Does that get me that? Okay. So that's kind of the algebra showing you that when I'm taking the 4th root, it's essentially taking the square root 2 times. Okay. If I was taking the 6th root, it'd be taking the square root 3 times, right? Okay. When we look at this, and the reason I want to talk about that is because of how we could maybe start isolating things here. Okay. And I'm going to isolate some stuff here that I think initially is going to not do anything for us. If I remember the route that we have to take here to do this. Yeah. So let's go root x minus 4 equals 3 fourth root of x. And this is what I was saying earlier at the beginning of the class, is that there will be times that in this course, we will do steps purposely, because I know them to be purposely done this way, so that we don't get something simpler. And we can always consistently think about what steps we're doing and what that's going to yield and whether it's going to be beneficial for us in the long run. We're always got to be thinking throughout the process. So I look at this and I think, okay, I know that looking at that, we're going to want to try to get rid of one of those radicals. Okay, so let's try. Actually, let's do it this way instead. Let's put the plus. I don't think that one's going to work. Let's put the plus 4 over here. We can do that, right? Because maybe we're going off the idea that we had to isolate the radical, and maybe we isolate the simplest radical. So if I wanted to get rid of that radical on the left-hand side, what do I need to do? Okay, square both sides, right? Perfectly fine. It works. If I square this, I'm allowed to do that. It gives me x. Now over here, it might be a little bit messy. Okay? So this is what we're doing here. It's a binomial, right? So you have to do your foiling process. So I'm going to take my 3 squared gives me 9, right? Okay. Now when I take root 4 of x and I square that, and it plays along with what we've got going on here. Root 4 of x squared, well that is the same thing as x to the 1/4 squared. Doesn't that give me x to the 1/2? Which is square root of x, right? So when I square this thing here, I get 9 times square root of x. That would be the f of my foiling process, okay? Last times last will give me 16. So 4 squared gives me 16. Now I gotta do O and I. Well, O and I, 4 times 3 gives me 12, right? I double that and gives myself 24, and then I've got that 4th root as well. And this is why, this step here is why I think it's always important to be thinking about what you're doing and what you started with. You started with a root, right? Square root and a 4th root. We go through some algebra. We go through that red algebra. Then we square both sides. We know that that's something to do. But what did I generate in that final blue line? A root and a 4th root, right? It did not get simpler. If anything, it got more difficult because now the coefficients and the constants are bigger numbers, right? Okay? So, that's why we've always got to be thinking, because I could work my way out of this if we do the right steps. But you could also continue to kind of do the game that we just did and make this even more complex and more complex and more complex, and you never get something simple. Is that all right with everybody? Okay. And that scares me, because people say, well, it didn't get simpler, so I did something wrong. You didn't do anything wrong. Those were 100% accurate steps. They worked. You didn't do any wrong algebra there. It just didn't lead us anywhere. All right. So that being said, maybe we do this. Maybe we, what I had initially was three 4th root of x, right? I think this maybe makes a little bit more sense. Let's go ahead and look at that. Now, you might not be a fan of trying to get rid of this 4th root right away, okay? You guys remember Pascal's triangle from last year? Okay, it was, we used it with something called binomial expansion. So the way I can get rid of this 4th root is to raise both sides to the 4th power, right? But then you'll have root x minus 4 raised to the 4th power. And if you remember binomial expansion, you did something like this. So this was a power of 2, okay? And that's Now those are the coefficients for, like, I think a plus b squared, right? Okay, the 1, there's your doubling your a and your b, and then there's your b squared. If I have 3, it's going to be 1, 3, 3, and 1. But if I have a power of 4, which is what we're dealing with, we'd have a 1, a 4, a 6, a 4, and a 1. And what's going to happen then is, so this is something like a plus b to the 4th. This is going to be a to the 4th plus 4a cubed b to the 1st plus 6a squared b squared plus 4a b to the 3rd plus b to the 4th. Maybe you remember doing something like that last year, right? Okay. So if I took the right hand side and raised that to the 4th power, that simplifies real nice. When I raise this to the 4th power, I got to do something like this, and that's kind of ugly, right? So I'm going to kind of do it in stages. I'm going to look at that 4th power, or sorry, 4th root. And do it in steps. Keep doing that. 3, 4th root x. I'm going to square this side first. And then square that side. Because I can get to the power of 4 through squaring as long as I do it twice, right? That's what I'm going to do. If I do that to the right-hand side, that's not too bad. I get 9. Okay? Now we've already done an example where we took the 4th root of x and we squared it. So the 4th root of x times the 4th root of x just gives me the square root of x. So that's nice. Okay? Now over here, radical x times radical x. So FOIL this gives me just x. Okay? O and I are going to give me negative 8 root x, right? And last times last gives me 16. Thinking about what we started with a 4th root and a square root. And now we did some work, and now we're just down to a grouping of square roots, right? It's simpler, right? So that probably signifies that we're on the right track to something. We're doing something right here. I think maybe adding 8x to both sides, or 8 radical x to both sides makes sense. X plus 16 is equal to 17 root x. Why would I do that? Because we have a radical, right? When we have radicals, we want to isolate them so we can undo them with their inverse operation. So I'm going to undo this radical by squaring again. Okay, so this is good. This is the second power of 2 here, second squaring process is ultimately finishing off the idea if we were to take and raise both sides to the 4th power. Doing this, again, doesn't create too big of an issue. It's going to be x squared. This will be 32x. And 16 squared is 256. Squaring this on the right-hand side, 17 squared is 289. Square root of x squared is just x, right? What's nice about that? It's quadratic, right? We go through and we say x squared, move my 289x over, gives me 257, negative 257x plus 256 equals 0. Hopefully you guys look at that. You can factor that quickly. X minus 1, x minus 256 equals 0. So then x is 1 and x is 256. Now remember, we started with roots, right? We need to check them. Check my 1. What's the square root of what? 1. Okay. What's the 4th root of 1? 1. So I have 1 minus 3 minus 4. Gives me negative 6, right? Does negative 6 equal 0? Nope. So it tells me that value of 1 is an extraneous solution. Does that make 256 an answer? No, not necessarily. Gotta check it. What's the square root of 256? 16. Okay, now this is what I like, because I don't know the 4th root of 256 off the top of my head. I don't have those memorized. But if I know that the 4th root is the square root of a square root, what's the square root of 256? 16. What's the square root of 16? 4. So you now told me that the 4th root of 256 is 4. So then that turned into minus 12. That's a problem. There we go. Wow. Minus 4 then. Is that a true statement? Yeah. So 256 is my only answer. Was that a lot of work? I think it was. Let me show you something real quick. It's the benefit of recognizing something looks quadratic. Can I rewrite that as u equals x to the 1/4 and u squared equals x to the 1/2? So then I get u squared minus 3u minus 4 equals 0, right? That factor is u minus 4, u plus 1. So u equals 4, u equals -1. Is that okay with everybody? What was u? X to the 1/4. So over here, we get the same answers because we're essentially raising things to the 4th power, right? And we did that through 2 processes of squaring. Over here, we still have to raise something to the 4th power. But isn't it so much easier to raise this thing to the 4th power here? Raise that to the 4th power. Raise that to the 4th power gives me x equals 16. Not 16, 256. 256. And -1 raised to the 4th power is 1 as well. Does that make sense? So we still do the same logic. We still have to raise something to the 4th power. It's just in the blue, it's so much easier. It's quicker. Okay? But all that same work is done in the red and black, but just kind of tweaked a little bit, looking a little bit. All right? And that's my suggestion to you, is not to be robots. Always be thinking about what am I doing and how is it going to benefit me, so that you can save yourself a little bit of time in some of your work. Okay? All right, so we're going to run out of time here. We got quite a bit further in the last class. We got to, I guess it wasn't the last one. They did 2 more questions. The assignment that is open right now in 1-6, that's going to shut off on Sunday evening. Fanny said I didn't maybe extend that yet for you guys, so I will do that. I might have done it for the first period, but I might not have saved for a second period. So I'll do that here momentarily. I apologize for that. But that's